Okay, awesome. Wanted to talk tonight about two things that I'm very excited about, which is Linux and RISC-V, and I'm going to get into that. I'm also going to talk about ways to use RISC-V and Linux on open hardware. So just to start off with, just wanted to mention what the definition of open source hardware is to me. So it's hardware whose design is made publicly available so that anyone can study, modify, distribute, make, and sell the design or hardware based on that design. So similar to open source software, but just in the context of the design files for hardware. So with electronics, which is mostly what I work with, this would be where you're sharing the documentation for your project, which would be the schematics, the board layout, which would be in the editable source files. So if you're using KiCad, which I use for designing boards, then it would be the KiCad files. The point there is if you want to enable people to collaborate on the project, then it's best to share the original files, not just an output file like a PDF or a graphics file. Or the Gerbers, because those are output files. And then also the bill of materials. And also best practice if you want to build a open hardware project that other people can help develop, then it would be good to make sure that the parts are available in low quantity. I talked more about this in a talk I gave recently at the Chaos Communications Congress. So by the way, at the beginning here, all the slides have a bunch of links in them, and you can get the PDF of my GitHub. Also just tweeted it from PDP7 on Twitter, so you can click on that as well. So want to talk about RISC-V. Maybe some of you have heard of it before. If not, I'm going to go over some of the basics of it. So when you write a C or C++ program, it gets compiled in the instructions for the microprocessor or CPU to execute. But how does the compiler know what instructions the CPU understands? So this is defined by the instruction set architecture, or ISA. So it's a standard that defines the set of rules for the tasks that the processor can perform. You've probably heard of ISAs like x86, which is Intel AMD, or ARM. So your desktop or laptop like mine is probably an Intel or AMD, so it has the x86 instruction set. And pretty much everyone's phones are going to be ARM, also Raspberry Pi and other single board computers are mostly ARM. So, but both of these are proprietary instruction sets, and they require commercial licensing to use. So RISC-V was created about 10 years ago by some computer architecture researchers at the University of California, Berkeley. The idea was to create a new instruction set that they could use for their processor research. And not have to deal with trying to license a commercially available one like ARM. So that was the idea here, was to create something that they could use for the research, and it's kind of growing from there. Two really good talks that I recommend checking out, because this is going to be kind of a short introduction here. One is from David Patterson, who's a professor at Berkeley, who was one of the people who originally created RISC back in the 80s. And then Kirsta Stanovich, which is one of the other professors from Berkeley, every year gives a State of the Union for RISC-V. So this link is to the most recent one. It's a good overview of the instruction set and how it's being used. And one time I got the question, what is the 5? So this is the 5th RISC instruction set to come out of Berkeley, going back to the original one back in the 80s, which stands for Reduced Instruction Set. The idea behind RISC-V is that it's simple. And they also started off with a clean design based on all the knowledge they'd gained over the decades with designing instruction sets. The idea is that it's going to be modular. So there's a core ISA, which is just 32-bit integer instruction set, and that's fixed. So if you compile a program right now for RISC-V, the base instruction set, that'll still run in 20 years on some fancy processor that has a bunch of extensions. So the idea here is to build something that can scale all the way from a little tiny microcontroller all the way up to a supercomputer. So that's the idea behind there, is you have one instruction set that can be extended in a modular way. And one of the important things when it comes to an instruction set is that you have software ecosystem around it. So the great thing is, over the past 10 years, there's been a lot of work on the software side done. So there's support in GCC, in LLVM, Clang, and also in operating systems like Linux and BSD. And some real-time operating systems as well. And there's also a lot of open source implementations, some from Berkeley, some from ETH Zurich, and there's also commercial implementations as well. So there's a nice mix of different implementations that you can grab, and also software support. Now, one of the things that's important to note, I think, is RISC-V itself is just an instruction set that's openly licensed under a Creative Commons license. So if something's RISC-V, doesn't necessarily mean that the entire thing is open source. There are proprietary implementations of RISC-V, but in order to have an open source processor, we need to have an open instruction set. So I couldn't go and design an open source processor that implemented x86 or ARM, because those are proprietary and I wouldn't be able to do that. So we need an open ISA if we're going to build open processors, though it doesn't necessarily mean it's open source just because it implements RISC-V. One of the exciting things is that it's being embraced a lot by industry. Originally, the instruction set was created by Berkeley. It's now stewarded by the RISC-V Foundation. And there's over 400 members now of that foundation, from companies to universities, nonprofits. One of the ways I've learned a lot about RISC-V is by watching all the talks on their YouTube channel. There's several events throughout the year that happen, so it's a good way to find out the latest things that are happening. And one of the other things that's exciting is companies like NVIDIA and Western Digital are investing heavily into RISC-V and are looking to use it in the products that they're going to ship. So with Western Digital, they have processors in their drives that handle all sorts of lower level tasks, and instead of licensing a commercial core, they're now going to be using RISC-V. So in the next year or two, they're going to start shipping millions of devices that have RISC-V cores in them. One, this allows them to save on the licensing fees, which if you're going to be making billions of devices, then that does matter. The other thing is it gives them the freedom to implement the instruction set the way they want, which is called the microarchitecture. And one of the things when it comes to ARM is there's a lot of companies that license ARM cores, but only a few companies like Qualcomm and Apple do an architecture license. So everyone else is just kind of stuck with however the core is implemented. So RISC-V gives these companies the freedom to be able to design the microarchitecture the way they want. And there's also several existing open source cores that you can leverage, like Boom and Rocket from Berkeley, Pulp is from ETH Zurich, and then Swerve that's actually one from Western Digital. So there's a growing number of kind of tested and usable cores that you can use in your designs now. And one of the things I've been excited about is Low Risk, which is actually it's a not-for-profit organization in the UK, and it was started by a couple of the people that were involved in Raspberry Pi, including Alex Bradbury. And their idea behind this was they wanted to create a fully open source system on chip that you could do something like base a single board computer around or a phone. That's still in progress with them, but they're more focused right now on doing some security related projects with Google called Open Titan. But hopefully at some point in the future, they might be able to fulfill that vision they had and be able to produce a system on chip that we could build a single board computer around. I wrote a column a few issues ago in Hackspace magazine that goes into a little bit more if you want to learn more. And just kind of, this is a very quick overview, so I'm going to be going through a bunch of slides, but although all the links are in the slides too, if you want to find out more afterwards. So some of the researchers at Berkeley ended up creating a company called SiFive, and they're producing core designs and also some chips that implement RISC-V. This here is one of their first, which is a microcontroller, and they sell this development board that's an Arduino form factor. So this is pretty cool. This is one of the first boards that you could get that had RISC-V on it. However, this is just a microcontroller. It only has kilobytes of memory. It's not something that we can run Linux on. So in this section, I'm going to talk about some of the Linux-capable RISC-V chips that are out there right now. So SiFive ended up coming out with a pretty exciting chip, which has 4 64-bit RISC-V cores. And it comes in the form of this board here called the Hi5 Unleash board. So this is a really awesome development board. It's got 4 64-bit cores. It's probably the highest performance dev board that you can get for running Linux on RISC-V. The unfortunate thing is it was just meant as kind of an evaluation thing for engineers, and it costs $1,000 and it's no longer available for sale. They might come out with a newer version, but it'll probably also be expensive, because the idea here is it's just kind of to be a proof of concept. The idea here is that companies would then use this core design and produce their own chips. But if you're looking for kind of the best performance to run Linux on RISC-V right now, it would be this board if you're able to get it. Now, some of the lucky people that do have it are people that are working on distro support. So there is a group of people that have produced a RISC-V port for Fedora. And this is an example here of that SiFive Unleashed board, along with some extra hardware to have a graphics output. And this is actually running a Fedora desktop here on that SiFive Unleashed board. So that is a little, that's nice if you have that hardware, but it's pretty expensive and hard to get. So another option is to use QEMU, which is an emulator that allows you to run any instruction set on your computer. So you can actually run the Fedora port in QEMU on your laptop or your desktop. The people that are working on the Fedora port are using both a mix of real hardware like that SiFive Unleashed board, and then also QEMU on big servers. And then in addition to Fedora, there's also a Debian port that's been worked on for several years now. So both Fedora and Debian have pretty good support now. But not too many people have this Unleashed board, and it was pretty expensive. So what are some options if we don't have $1,000 to spend on a dev board? So this board here is from a company called SiFive, and they're using this chip called the Kendrite K210, which is a really affordable board. It's only a $13 board, and it can boot up Linux. However, it is limited to only 8 megabytes of SRAM, which is not a lot for Linux. So this is a pretty powerful chip for a microcontroller, but not great when it comes to Linux, but it does run Linux. So a couple of people, including Damien Lamal at Western Digital, did a bunch of kernel hacking and got Linux to run on it. So you can right now go buy this SiFive Max Bit board. It's only $13, and you can go and boot up Linux on it. So it's a fun way to experiment for not a lot of money. Here's an example here of showing it runs. It's running the mainline kernel at the time. So it's got dual 64-bit processors, and it actually has a little C compiler that you can run it as well. There's another version of the board that inside of that has one of those ESP Wi-Fi chips. So potentially you could actually have networking in it. But again, the 8 megabytes of SRAM kind of constrains what you could do. So this is a great thing to get and play around with RISC-V on Linux right now. But it's not the sort of thing that it's going to match like a single board computer like you might be used to. Though you can just if you buy that board for $13, you can go and download this image and throw it on there, and you'll have Linux booting up on it. So good thing to play around with. But what I would like is something that's similar to a BeagleBone or a Raspberry Pi that's RISC-V. So in order to do that, we're going to need a more powerful chip. So one of the possibilities is Microchip has this PolarFire system on chip, FPGA, which has a hard RISC-V core inside of an FPGA. So if you've heard of the Xilinx Zinc, it's kind of like that. But because it has an FPGA in it, it's probably going to be a little bit more expensive than we would want to build something like a $100 or less board. The other thing that's quite exciting is there's this group called the OpenHW group, and they're working with a couple different companies to try and produce a open core that has like real peripherals that we can use. So you might be familiar, there's a pretty popular chip when it comes to embedded Linux is the NXP, formerly Freescale IMX. So the idea here is taking the ARM out and replacing it with the RISC-V. And this is something that's slated to tape out, which means fabricate by the end of this year. So probably is not going to be something, if it works out, to be a product until maybe next year, but this is kind of the sort of chip that we would need if we were going to build a single board computer that would have performance similar to like a Raspberry Pi or a BeagleBone. But this is pretty exciting. We'll have to see what happens with that. So basically, we have the SiFive Unleashed, which is pretty expensive and hard to get. We have the Kendrite chip, which is pretty affordable, but not a great target for Linux because it only has 8 megabytes of memory. So one of the things that we can do right now is we can leverage FPGAs also to run Linux on open source hardware. So if you're not familiar with FPGAs, there's a great talk from SuperCon last year, Hackaday SuperCon, by Dr. Megan Wachs of SiFive, and it goes over some of the basics of FPGAs and how they're being used to build systems. So FPGA stands for Field Programmable Gate Array. You can think of it as a sea or ocean of logic blocks inside of a chip that are able to be configured. So we can take those logic blocks, which is a bunch of gates, and reconfigure them to be any digital logic that we want, including a processor core. So when I first used FPGAs back in school a while ago, it was all proprietary tools, and I had to run Windows, which wasn't very fun. And one of the cool things that's coming along in the meantime is that there's now an open source tool chain for a couple different FPGAs. And this was due to Claire Wolf and a couple other awesome hackers that have gotten these tool chains working, open source tool chains working with FPGAs. So the first one was this Lattice ICE40, which is not a big enough of an FPGA for us to be able to implement a RISC-V core that can run Linux. But the next bigger FPGA from Lattice, the ECP5, is. And it also has an open source tool chain thanks to David Shaw, who's actually, I think, located in London. I actually met him at the open source hardware user group in London last year, I think it was. So thanks to that, you can actually, using only open source tools, have a RISC-V core that can run Linux inside of an FPGA. And one of the things on the horizon is much more powerful FPGAs are from a company called Xilinx, and there's some people that are working on open source tools for that, which will allow us to even have much more capable systems running Linux on a RISC-V processor. And if you're new to all this FPGA concepts, I wrote an article on Hackspace magazine a few issues ago, which I recommend checking that out. And there's some links to some more things, other resources. So I wanted to talk about specifically a project that I was involved in. So last year at a hardware hacking conference called Hackaday SuperCon in LA back in November, this was the conference badge. So if you've seen conferences now, a lot of them will have electronic badges that you can hack on during the conference. So the idea here was a Game Boy form factor, and it came with a C engine for the graphics that you could use to program games, and it was pretty fun. You could do animations and have Tetris and all our games like that. But a couple of us thought, hey, let's try and see if we can get Linux on it. So this has the ECP5 FPGA from Lattice, which is supported by the open source tools I just mentioned. So, and it has enough of those gates, in this case, 45,000 gates, which is enough for us to configure it to be a RISC-V core that can run Linux. So this is some of us sitting there hacking on it over the weekend at SuperCon back in November. There's a blog post I wrote with some more information. The first thing we tried had built-in memory of 16 megabytes, but we couldn't get it to work at the time. However, someone actually, because it was a hardware hacking conference, had already made an expansion board for the badge, which gave us 32 megabytes of SD-RAM, which proved to be enough for us to be able to get Linux running on it. So the front there was kind of that Game Boy form factor, and the idea here was on the back it had an expansion slot to kind of be like a game cartridge slot on a Game Boy. So this is a board that actually plugs into the back of the badge here, and this gives us 32 megabytes of SD-RAM that we can access. So I was talking about how you can configure these logic gates to be a processor core. So here's a interesting kind of macro view of what it looks like when we zoom out and we've configured all those 45,000 something gates to be a processor. So this is kind of what it looks like at a macro level. And the fact that we're not using all the logic too, so we still have room to implement other hardware functionality if we wanted to. So how did we get that badge with the FPGA actually running Linux? And one of the ways we did that was by using Python. One of my friends, Tim Ansel, he gave a great talk about how you can use Python to actually design hardware, not just run on hardware, but actually use it to design hardware. And one of the reasons for this is that I use Python a lot. It's a powerful language. I think it's a productive language, like Tim does as well. And I come from a software background, and I'm not as familiar with the languages that people use to design chips, like, or hardware logic, like Verilog or VHDL. So for me, Python's a more natural language to work in. And I think because there's probably more software engineers than hardware engineers or chip designers, in general, this is a good way to get more people involved. So here's an example. So when it comes to FPGA design, people are usually using what's called the hardware description language, or HDL, which is basically a text description of how we want to configure the digital logic. And one of the examples is Verilog. It's very common, or VHDL. And this is, instead of using those languages, it's using Python instead, thanks to a framework called MeeGen. So this is an example. If you worked with Verilog or VHDL before, you might see kind of the similarities. Well, not in the syntax here, but kind of the concepts here. How we have a counter, and then we're using one of the bits from the counter to turn on and off an LED. So this is just a little snip of what it looks like. And on this slide, I took this from the FPGA 101 tutorial from LIDEX, and recommend going through that as well after this at some point if you're interested. But on the left here, we have an example of what Verilog looks like for a basic digital block, which is a flip-flop. And on the right here, we have the implementation in MeeGen, which is the Python-like language. So in addition to MeeGen, we use this thing called LIDEX. So LIDEX is this framework that gives us a bunch of IP. So when it comes to the hardware world, when you think of peripherals like DRAM controller or USB controller, those are typically called IP, as an intellectual property, which you could also think of it as a library. So LIDEX gives us these different IP modules. Let me jump ahead here. Yeah, so things like a DRAM controller, Ethernet controller, PCI controller, we get those things out of the LIDEX framework. Now with the badge, all we had was DRAM and serial port. So for us, we weren't using that much. We just used the LIDEX serial IP module and the DRAM controller. And just to break this down a little bit here, so LIDEX, we can use to build a full system on chip that goes inside of the FPGA, which is what we did. And LIDEX itself is based on MeeGen, which is that Python framework that allows us to do hardware description language in Python. And putting that all together, we actually can make a little system on chip here that we can load into our FPGA that can run Linux. So we're using a sub-project called Linux and LIDEX, VEX RISC-V. So VEX RISC-V is an open source implementation of a RISC-V processor. So we combine that with some of the pieces from LIDEX, like light DRAM, so we can talk to our memory. In this project, if you download it, run the make and everything, it'll spit out something that you can load onto your FPGA. So basically, by taking these different pieces, we can pull them together and give us a full system that we can load onto the FPGA. So this is what it looks like when I have the serial port connected on the badge to my computer and a terminal emulator, and we can see Linux boot up there, and I can type in the prompt there. In this case, it's just running BusyBox, so not anything that too interesting happening, but kind of a proof of concept that it's running Linux. So after we got back from the conference, thought it would be a good idea to try and upstream all the hacking that we had did into the LIDEX project. Now this is probably not too useful to people because only people at the conference had the badge, but this is, I think, is a good idea of how you would add your own board potentially to LIDEX. So if you have an FPGA dev board and you wanted to add it into the LIDEX project, this is an example of how you could go about doing that. And also, I included this to give you a bit of a flavor of what LIDEX in that MeeGen syntax looks like. So instead of, this is something called a pin constraints file. So this is listing all the different pins or balls on that FPGA, how they're mapped to the different peripherals on our board. And this is what this file is describing, and it's in Python syntax, which to me is easier to work with than Verilog. This is also kind of giving an idea of what it looks like here. So this is the Python file that defines the different pieces that we're pulling in to build our system on chip, which to me, and I think so other people involved, this is easier to look at than some big Verilog file, because I understand the Python syntax better and the object-oriented nature of it and the fact that we can import modules. So to me, this is much easier to work with than a corresponding Verilog implementation. And give you an idea here, this is from the file that is the make file, essentially the Python file that builds the bit stream, as it's called, that goes onto the FPGA. And we just took an existing board that was using that ECP5 FPGA and just modified it to what we had on our board. And another example here of how Python makes it easier, in my opinion, to work with than Verilog is we had a DRAM chip on our badge that was not already supported in Light DRAM, which is that DRAM controller that's part of LightX. So in order to be able to use that DRAM chip, we need to add it in. And this, I think, is a nice example of the object-oriented and modular nature of Python. So here, I just have to extend that SDRAM module and then just basically plug in the numbers there that we had from the data sheet for the DRAM chip that we were using. So rather than having to implement this whole thing in Verilog, leverage the object-oriented nature of Python and just extend it with the things that were specific to our project. And another kind of neat thing, and if you get involved with playing around with LightX, Enjoy Digital is his username. His name is Florent. He's really awesome to work with and very responsive. So we had Linux running, but it took 300 seconds to boot, which is not very fun. So I opened up an issue on GitHub, and the next day, or actually within a few hours, I think he had given me a fix to make it go 10 times faster. So I thought that was a pretty fun kind of example of opening up a pull request and being very impressed with the results. And again, to just show you that, in my opinion, the reason it's nicer to work with Python instead of Verilog is this is an example of one of the optimizations he did here. And I don't know a lot about the design of it, but since it's in Python, I can look at this and kind of get an idea of what's happening here. In this case, to make it run faster, he made the cache bigger, so we'd have to go to memory less. And I can kind of glance at a bit looking at this diff. So to me, I think it's really awesome to be able to use Python for hardware design. And you might have noticed there was a display. Eventually, Greg Davil, who's a really awesome hardware hacker in Australia, eventually got the display working. So we finally now have the terminal booting up, and you can see it on the badge. So there's kind of a fun project that increased my knowledge of FPGAs and RISC-V a lot, and I think there are people involved with it. Real quick, if you were not at the conference, you don't have this badge, but there are 2 open source boards that you can get if you want to play around with RISC-V and Linux on this FPGA. So one is from a hackerspace in Croatia called Radiona. They just did a successful campaign on crowd supply. And the other one is from Greg. It's called the Orange Crab. And this also just was successfully campaign on GroupGet. So both of those are 2 open source boards that you could get and play around with this more. And one of the things, though, I'll say is Linux is not necessarily the best place to start. So if you want to just get started with the whole idea of FPGAs and kind of build up your knowledge from a more fundamental basis, this is a great board you can get. Also an open source board called the FOMU. It's an FPGA that is supported by open source tools and has enough to implement a basic RISC-V microcontroller. And you can learn a lot more by going through those workshops that they have for it online. And if you don't have any hardware, you can actually use this great program called Renode, which allows you to basically simulate this hardware, these FPGAs on your computer. So for example, I mentioned the SiFive Unleash board that we can run Linux on. We don't actually need any hardware. We can actually download Renode and run through the tutorial here. So this is me on a train running Renode, which is simulating that SiFive Unleash board. So I'm actually running RISC-V in this simulated or emulated RISC-V processor, and it's behaving the same as if I'd had the actual board in front of me. So that's it. There's a bunch of links in the slides you can get from that PDF there. And if we have time, happy to take questions.
Yeah, I mean, I'll just drop in there. Unfortunately, I dropped out midway through your presentation, so I missed a little bit of that. But
Okay.
no, I got the bulk of it. So yeah, really, really fascinating stuff. Do you know anything at all about the rumors about Pi 5 actually being a RISC-V architecture? Because there was rumors about Pi 4 was meant to switch off from ARM. And then when it came out, obviously it was another ARM chip. And so I just wondered if you do you know anything?
I do not know anything directly, but if I can get back to that slide. So Low Risk is a organization that was started maybe 5 years ago. Forget the person's name. It was one of the original board members of the Raspberry Pi Foundation and also one of the grad students, Alex Bradbury. So their goal has been to produce a open source system on chip that's powerful enough to do something right, like run Linux on a single board computer. So I don't have any knowledge of what's going to happen, but I hope that would be awesome if it is. One of the things to note is it just kind of takes a long time to actually get silicon system on chips made because you only really get one shot, and for any sort of modern process, the masks are really, really expensive. So it's unfortunately taking a while to get an affordable chip that we can run Linux on and have something like a Raspberry Pi or a BeagleBone. So hopefully Raspberry Pi Foundation has something like that in the works. If not them, I think at some point, probably next year, we'll start seeing RISC-V processors that are capable of running Linux to do things like single board computer or like a basic smartphone. This initiative here from the Open Hardware Group, this is a test chip that's going to be taped out at the end of this year, which, if that becomes a product, would be something that would be capable of running Linux and have because it's I think a dual or a single 1.5 gigahertz RISC-V 64 bits. So, I think we're getting there. One of the things I do a lot is I keep my ear open to hear what's happening. And there's also some companies in China that are working on some new system on chips that might be suitable. So
yeah,
I don't know this year, but maybe next year.
Yeah, I mean, it's just something I keep hearing the rumors about, because I don't know if you've heard of RISC-OS at all.
Yeah, was that the thing that originally ran back on the old
on the original ARMS? Yeah.
Yeah.
I'm not part of a company, but I actually work as a contractor for the current IP rights holder for RISC-OS. Oh. And I've been having the chats behind the scenes. We've just launched a new version called RISC-OS Direct for the Raspberry Pi. And there's been lots of sort of talk about, well, what happens when the Pi jumps onto RISC-V, like they kept saying it's going to? What do we do? Because everything's still compiled for the ARM chipsets. So there's been a bit of, do we need to sit this on top of a Linux shell and then sit our OS on top of that? So that's kind of why I asked the question, and I'm just putting the feelers out there to see if someone knows something I don't.
One of the things that's nice is the software ecosystem is really advanced. So Western Digital in particular, basically Western Digital and SiFive have done a really great job on the Linux kernel and on the toolchains. So once we finally have chips that are available, the software support will be there. And I think it really just comes down is we need a company or an organization that's willing to put up the money that you need to be able to get a mask made. So we're talking about millions, if not tens of millions.
Yeah.
So it's really just going to take, and eventually it'll happen, but just have to be a little patient, I suppose.
Okay, well, that's great. Well, thank you very much for your time for answering that. And I said I'll hand back to the floor.